Good morning, everyone. It sounds like the audio is working okay. The video is working okay. Wonderful, wonderful. So today I'm going to talk about a Lytro product, Lytro Immerge, which is a virtual reality cinema product with the unique capability of allowing full 6 degrees of freedom viewing. Before I launch into that, though, let me just give you a little bit of history and background. So, Lytro is a 10-year-old company. I've been working at Lytro for 7 years. During that time, we've built a lot of technology for capturing, processing, playing back light field imagery. I'm showing a couple pictures on this slide of the consumer products that we did. Some of you have heard about these from me in other talks I've given at Beijing Film Academy over the years. The original light field camera in 2012, the Lytro Illume with a 40 megapixel sensor that was actually capable of generating pretty compelling light field images. Over that time, we built the company up to about 100 employees. We have a pretty substantial IP portfolio, but we made a change in the business about 2.5 years ago and switched from doing consumer products to doing professional products, which has been a lot of fun, and as it turns out is also very apropos for this audience and this Beijing Film Academy. So the Lytro Immerge briefly fills a position in the market that's unique at the moment. It is more fundamentally immersive for VR capture than the standard 360-degree kind of videos that many of you have seen. It's more fundamental, has higher image fidelity than what you can get by doing 3D rendering, even with the amazing things that today's game engines can do. So last year, when I talked about this product at this very conference, I showed these slides, which is a sort of animated way of illustrating what I mean by 6 degrees of freedom, the fact that the viewer's head can move arbitrarily within the view, and at all times the view that the viewer sees is correct for that position and that orientation. And to do that, we capture the light field within that viewing volume, right? So as long as the viewer's head and eyes stay in that volume, then the viewer experiences the correct perspective and even the correct lighting. That's all I could show you last year. This year, I can show something that's a little bit more compelling. So what's on the screen in front of you is, on this video, there's someone in an immersive experience with the VR headset on, and then on the lower right, there is a screen that's showing what one eye of that headset is also displaying. And I just want you to watch carefully, and you'll see the effect. Well, as he moves his head, you'll see the effect that it has on the image. So right in here, see, moves forward, moves backward, tilts sideways. Doesn't make any difference where he moves his head. The image that's being created is exactly correct. Let me just see if I can do that one more time. Yes, okay. So as he moves forward, the view moves forward, back, sideways. So that's the actual implementation I couldn't show you last year. Likewise, last year, there were a lot of questions about who's using it and what are they doing that couldn't be answered. Now, those questions, at least for this current year, can be answered. There have been 2 full live-action productions, 1 full computer graphic rendered production, and these things have been very well received. The one called Hallelujah, the first one, let me just quickly go over it's been viewed a lot of places very, very favorably. Note in particular that it is currently being viewed at the Museum of Contemporary Art in Montreal at the Leonard Cohen exhibit. This is a Leonard Cohen piece of music that is being done, and so they were particularly impressed with this. So a lot of progress since a year ago. Let me first just review a little bit of this business of light field. This will be a high-level discussion. We'll get more technical a little bit farther into the talk. So basically, ignoring light field, the choices you have for reproducing, for having an immersive experience boil down to 2 things. The experience can be created by modeling, standard computer graphics, build a model of the elephant, render the model of the elephant. This works really, really well for the parallax sense of immersion. 6 degrees of freedom, no problem. Computer graphics, we can render the elephant as easily from one position as another. When we do the lighting, will be correct for that position. It's great for those purposes. Now what it says here is that it has low realism. Well, that's not quite fair. Like you know that modern game engines can do remarkable things, but they're still not as good as cinema, and in cinema it's still very challenging to convincingly actually model people in a way that fools the viewers. It's not impossible perhaps in cinema at this point, it's impossible in game engines at this point. So that's one way to do immersion. The other way is to capture images and play them back. Unfortunately, that experience, by and large, is an experience that's limited to basically a single center of perception. There are some tricks that get a very rudimentary form of binocular parallax in these things, but they can't really do a view volume. When you move your head, the world moves with you. And that's actually at this point, I can't stand that anymore. So I really, really think that one of the huge advantages of this 6 degree of freedom immersion is just the comfort of viewing. You feel like you're in a world where the objects are sitting still and not moving with you. So those are the two standard choices. Light fields provide the third choice where we can have our cake and eat it too, where it's possible to have the fidelity of imagery and also have the 6 degree of freedom sense of immersion that you get with the geometric rendering. And by doing that, we give people an alternative to not have to make that artistic trade-off of having it either less than convincingly real or less than convincingly presence-like. So that's how Immerge positions itself in the market. So I mentioned that we've done several productions. Our goal as a company is to make our customers satisfied and happy, and I can report to you that so far we've been able to do that. And so I wanted to talk to you a little bit about the feedback we've had and why they like working with Lytro. I think if you had to boil it down to just one thing, it comes back to this issue of being able to reproduce human beings extremely convincingly. Right? It's hard to do, it's very difficult, I think impossible to do with pure geometry today. It's hard to do even with imagery, and we're successfully doing that. So if that would be the single most important thing, but there's more. For example, being able to do those extremely convincing humans, but also have that sense of presence, that palpable sense of being in an environment that is rigid around you and that you can therefore move closer to, farther from, look at things, change your viewpoint, and it all just stays right where it's supposed to be. That sense of presence is extremely powerful. We do that by getting the head parallax correct, so the view is correct where you move your head, the binocular parallax correct. Once you can get the parallax correct for a given view, binocular is just doing it twice. There's nothing really hard about binocular parallax at that point. And then finally, getting the view-dependent lighting to be correct. Remember, for things like faces, trying to model them as simple reflectances or simple BRDFs doesn't work. There's subsurface scattering. There are a lot of complicated lighting effects in human faces, especially around the eyes. Trying to model all that at game engine rates is essentially impossible, but capturing it with images and playing it back with light field technology works. So now here, I'm just going to show off a little bit about what I mean by view-dependent shading. This is not done with our system. It's just captured video, but you get the sense, right? These highlights move, and in a real sense, as I mentioned last year, the highlights are just another form of parallax. You're an expert at figuring out whether the highlights are moving correctly or not. They move differently than the objects, but they move in a way that's consistent with the lighting properties of the scene and of the object being illuminated. And if they don't work right, you can tell. So getting all that stuff is right is really, really important for a sense of presence and immersion. Finally, I'll show you the rig in a few moments, but the rig has almost 100 cameras on it, and we use them multiple times. So by the time we're done, we've captured on the order of 500 views of a scene that we then synthesize into this light field and play back. As a result, we can do our analysis in a much more robust way than if you've just got a handful of cameras. So we can deal with real cinematic lighting of the scene in ways that simple binocular systems are much less robust to and much less capable of doing. And then finally, something I think would be near and dear to a lot of you in the audience is that the system from the ground up is designed to be used by professionals in ways that they're used to doing things. A couple things to point out. One is that the camera, you'll see in a moment the physicalness of it, allows the person using the camera, the director, to sit behind it and view the scene as it's developing, to interactively see the views of the different cameras, typically the extreme views like you're seeing here, to see exactly what's being captured. And then the subsequent post-production all works with industry standard tools, typically Nuke. So we have a whole bunch of Nuke plugins, and the people who develop them at Lytro are people who've used these things year after year in industry, so they know exactly how they need to be used and what we need to do to make the whole system effective for professionals. And the net result is that it works very, very well for capturing and doing post-production. Remember, the core thing that's being captured here is imagery, and so it's a very comfortable fit to a standard post-production facility. So these are reasons why the people we work with enjoy working with Lytro and are successful working with Lytro. Okay, let me show you the rig. So here's a picture of the current rig. I'll point out, this slide used to say with Immerge 1.0, it's our intention to make a variety of rigs, just like standard cinematic capture involves different lenses and sometimes even different cameras. That's going to make sense for cinematic light field virtual reality capture as well. So we have plans for several different rigs, but I'm describing the one that was used to capture the imagery for the productions that I've mentioned to you. So, and this is a planar capture system, which might be a little surprising. Like we're capturing a volume of light, what we're doing with a plane. The way we do that is we actually, the planar system has a limited field of view, and we actually have to capture the scene in 5 separate takes. Right, so, and having done all that, then all this information, almost 500 camera views, is synthesized together into a single light field that is accurate for any viewing position within a volume we call the viewing volume. It's a little less than a meter in diameter. Right, so it's all the movement I've done on this stage so far, which admitted is limited. I'm not walking around, but I would have stayed inside that viewing volume. So if I was looking at you in this way rather than physically, you would have looked correct to me all the way through. Probably the lights would be up a little bit. So you might think, well, that's quite a constraint. A lot of us think of capturing 360 video with a 360-degree field of view capture system. And indeed, that's possible, but it turns out that it's not actually very practical for professional applications for reasons that you can probably tell me more about than you, but I'll just mention a couple of them. One is it allowed, by capturing just a limited field of view, it's possible to have control over that separate from the rest of the environment, in particular to be able to do lighting. I'm probably not going to show a complete video here today, but if I did, you would see that there's a lot of fancy lighting happening behind the camera, as you would see on any other set. Right? But you can't do all that fancy lighting if the camera is capturing 360 degrees. So having a limited field of view capture has been less of a concern than we expected initially. That said, 90 degrees isn't enough. Right, so we certainly have plans to do capture systems that are closer or perhaps exceed 180 degrees, but we're relatively uninterested in doing at least high quality capture for an entire 360 video. For professional applications, it makes more sense to piece these things together. A couple technical notes. One is that the planar array actually keeps the cameras far away from the edge of the viewing volume, which means that it's easier to allow objects to get closer to the viewing volume and still remain in focus with the cameras. Right, so there are some real practical advantages to doing a non-convex rig like this. A planar rig is one example of a non-convex rig. Okay, so now I want to dig in a little bit more on this whole business of 6 degree of freedom playback. This is the part of the system that I've done most of the architecting on, so this is a comfortable part of the talk where I can get a little bit more technical. So what I'm going to just say flat out is you can't do this by stitching images together. You can't do this by warping and distorting images. These approaches, these sort of classic image-based algorithms, simply will not produce a convincing result. What you need to do is, one pixel at a time, build the headset image by choosing the right pixels in the camera images and bringing them together, taking advantage of some information that's been computed along the way to make each final image. This is the only way to get the kind of result that is really desired here. The way we do that is called reprojection. It's expensive, but it's essential. And it's a light field approach. The payoff is, if you do it right, then everything works right. The way I like to think of it technically is all the parallax cues are correct. The head position cues, the binocular cues, the view-dependent shading cues, everything about how it would have looked from a viewpoint is accurately reconstructed. That's our goal, and that's what we set out to accomplish. So in order to understand reprojection, it's useful to start by just reviewing what we mean by projection. So what I've got up here is a very simple camera model, and I'm just going to talk about one point in the 3D scene, right? So this is not a realistic thing, but it's good for understanding what's going on in the system. I noticed after I drew this and was reviewing my own slides that I drew the camera the way a computer graphics person draws a camera, with the image plane in front of the center of perspective, because mathematically that's easier. A physical camera works the other way. It doesn't matter for the argument here, so I'll stay with this. So simple planar projection camera. And just a side note, ultimately we can't be doing planar projections in a system that does 360-degree fields of view, but to keep this simple, I'm just doing planar projections here. So how do we project that 3D point in the scene onto the camera image plane? Well, we do two things. We cast a ray from the center of perspective through the point in the scene, and then we compute the intersection of that ray with the image plane, and that is the projection. Mathematically, projection is a reduction in dimension. So there was a 3D point in the scene, it's become a 2D point on an image plane. That's a projection. That's how cameras work. Okay, so having done that, now we want to create a new view. So I've left our original camera here. We're going to compute a new view. How do we go about doing that? Basically, three important steps. First, the biggie. First one is we're going to go through every pixel of every camera image and compute the distance or the depth from the camera to the object in the scene that illuminated that pixel, to the 3D scene point. We compute all those depths, and that's a lot of work. Right? But remember, we have a lot of camera views, and so we can do that, and we can do it rapidly, even when there's... Am I doing anything wrong that's causing the audio to drop out, or can people hear? I'll keep going, but if you can't hear, I don't know, yell out. So we need to compute those depths for every pixel of every camera view. All right, so we'll try it this way. That sounds better to me. I'm going to hold this close to my mouth. Remind me if I forget. Okay, so once we've done that huge chunk of work, which is all done as part of a pre-processing step, right? And it doesn't actually happen during playback. Then the second step is to just do the projection in reverse. So we know where the center of perspective is. We know where the 2D projected point was. We know the depth. Those things together allow us to recompute, this time mathematically rather than optically, the 3D scene point. And then once we've got the 3D scene point, we can just project it to the new view, compute the new intersection, and we're done. We call this a reprojection because it's a projection from data that was already projected. So it's a second projection. And that's the core algorithm for what happens in our system during playback. One other note, there's an interesting property here called the reprojection angle. The angle formed between the rays from the camera center of perspective and the ray from the view center of perspective. In this simple diagram, that angle is huge. It's unacceptably large, right? And there are two reasons. So it's always better to keep that angle smaller. That's a fundamental reason that we have so many cameras on our rig. Why do we need a camera every 10 centimeters? Why do we need 500 cameras to capture all this information? Because we want to keep that reprojection angle small. If it gets large, lots of bad things happen. I'll just mention two. One is if there's any error in the depth at all, then the reprojection ends up being in the wrong place, right? And you can see how that's a pretty strong property of what the angle itself is. And then the second thing is that, remember, we're trying to reproduce view-dependent shading. But those views here have very, very different angles to the point, and consequently they would have very different shading effects if there are specularities or reflections or anything interesting going on. So we wouldn't be able to reconstruct well if we did things with large reprojection angles. So this illustration has a huge angle because that makes it easy for me to draw, but that's not how things actually work. In practice, these angles are kept very, very small. Okay, so that's an overview of how reprojection works. I'm going to take a few minutes here without getting in too much detail and just talk about why it's hard. So I'm going to list 7 reasons why it's difficult to do. The first one is something that we and I think a lot of others call disocclusion. This is a very simple problem. As you can tell by just moving your head around here, when you look from a different position, it isn't just that things look a little different. Things that you couldn't see before come into view. Consequently, when you reproject one image to another at a different viewpoint, there are things in the new image that weren't in the original image. They won't show up. The only way to fill in those voids, those disocclusions, is to reproject multiple camera images which have different viewpoints, typically surrounding the viewpoint that you're trying to create. It doesn't take very many usually, so I just say up here, we're going to need several cameras in order to handle those disocclusions. Of course, you can think of fiendishly difficult situations, but generally several works. So good. Unfortunately, not so good. Here's where it gets more complicated. We want to do view-dependent shading. Remember, that means we need to keep that reprojection angle small. Well, if the view you're trying to recreate is near a camera, meaning its center of perspective is physically, mathematically at least, close to the center of perspective of a camera view, then that camera view can provide good pixels or rays for most of the new view. But suppose the new view isn't near any of the cameras. So considering our planar rig, suppose that it's near the front of the view volume instead of in the plane of the cameras. It's quite possible that you need all of the camera images to create one headset view. So it's not that you need them all for one pixel, but you need them all to create a single headset view while simultaneously ensuring that you don't have large reprojection angles. That's hard, right? That's complicated data management system required to be able to do that. The third thing, ideally, there would be a right place to put a pixel. Remember, in my drawing, I talked about points. I didn't talk about pixels. But cameras don't actually capture points, they capture pixels. And that pixel has its own small solid angle, and it may actually view multiple objects in the scene. It hits a silhouette of something close by, so part of its color is from the nearby object, part of its color is from the farther object or a background. Uh-oh, what do you do with that? Right? That's hard. It's hard. If you do it, if you reproject it with either the depth of the near or the far object, some color is going to end up in the wrong place. And the bigger the reprojection angle, the more wrong place it's going to end up in. Right? Another reason to keep that angle small. But this is a serious problem, and there's a lot of technology in our systems to deal with this. Fourth one, spatial continuity. If I move like this, it won't do to have things suddenly change color. Right, and so I'm going to have to do what is done in computer graphics over and over and over. The standard solution is, we sometimes call it lerping in computer graphics. We're going to interpolate. We have to interpolate. We can't make any sudden changes in how we do the reprojection based on the head position, or else we're going to get caught. You're going to see it when you move your head. We don't want that. I didn't even mention temporal continuity. That's hard as well. Image resolution. To be convincing, we need a lot of pixels, and in order to get the view-dependent shading right and all this parallax right, we need a lot more pixels. Remember, there were 500 camera images captured at 30 frames per second. It's quite a mountain of data. So we'd have to support these huge amounts of data and the substantial bandwidths that are required. And we have to do all that at frame rates that are accepted by modern headsets, which I think at this point is a minimum of 90 frames per second, and it's going to get higher rather than lower, right? So it's an amazing amount of computation. Remember, every pixel of every frame has to be computed by pulling together the right pixels from the camera images. And then finally, here I've written should instead of must, because it turns out that the things that we've distributed this year don't do this, right? The videos, the immersive experiences that our customers have seen so far this year do not correctly anti-alias silhouettes. Right, and those of you who know about computer graphics recognize that that's sort of a crime, right? I mean, it really isn't acceptable these days to not do good sampling. So what I want to do is switch from that section to talk a little bit about new product, Immerge 2.0, that was introduced just earlier this week, so you're hearing about it right away. This is the result of work a lot of us, certainly including myself, have been doing for the last year. So really two exciting things have happened. One is we've been able to push the fundamental image resolution up substantially. So here, the actual way we store images in our system is in equirectangular projections. That's why they look distorted here, but they get put back together appropriately. This is the kind of non-planar projection that's required for large fields of view. So, and this just models the relative change in the number of pixels. So at 5K, we're the market lead in image resolution. And this makes a real measurable difference. If I could put you in a headset, you'd be able to see this difference right away. So, but this is mostly just a plumbing and bandwidth challenge. It's relatively uninteresting technically, not to say it isn't hard. What's more exciting to me is that we have been able to solve this anti-aliasing problem. I'm putting up these big simplistic pictures because you can actually see, those of you who aren't familiar with what it looks like when things are anti-aliased, it's not that there are more pixels, it's that there are better pixels, that the pixels along an edge have their colors blended between foreground and background in a way that collectively causes the edge to appear smooth. Those of you in the back, the edges in the rightmost image might actually appear smooth. I hope not. I want you to be able to see the individual pixels. By the way, these images are taken right off my development system, which is sitting on my laptop in the front row. But to show off better, in the Hallelujah video, I don't know if you'll be able to see this, but the image on the left is in the current state. The image on the right is anti-aliased. I've circled a region that is particularly easy to see the difference. I'm going to play this video, and those of you in the front at least can probably see that it looks kind of jagged. See the ripples moving up and down through the red circle. If you compare that to the green looks a lot better. We'll go back and do it again. Oh, well, yeah. Is it? Yeah, doing it again. And then I will also just point out that we'll do this again for the area under the singer's right arm, which is what we have learned to call a keyhole. Right, it's sort of like Alice in Wonderland looking through the keyhole. These are some of the most difficult things to deal with because the background is occluded almost anywhere you look. It's quite possible in extreme cases that no camera captured parts of the background. If the keyhole is close to the cameras and the angles end up being high, you might not have anything to put in that background. So these are really interesting challenges. Again, we'll just play this back, and those of you who are close at least will be able to see the difference in jaggedness on the left. All of this is immensely obvious when you have your head in the headset, and it makes a huge difference, again, to that sense of actually being there. Right? The parallax is right, the shading is right, and now you're not seeing these time and motion and false motion artifacts that result from animated anti-aliasing. So I've just been really excited and satisfied to be able to get this technology in. At this point, I see no fundamental reason why we can't move the system progressively toward true cinematic playback quality, whatever exactly that is. There are no fundamental things in the way. That's where we're headed. And with that, I thank you for your attention, and there's a chance maybe I can take questions. We'll see. Thanks.